one of the issues with CDMA is clearly that everybody is talking at the same time, the same frequency band. In other words, the frequency reuse factor is 1. And how do we deal with the resulting interference? Interference in the air for cellular network is the first example in this course of something called negative externality. Externality here, roughly speaking, refers to the fact that your happiness also depends on what other people do. Okay? Your signal, your cup of tea or coffee is other transmission's poison. And this is what we call a negative externality. Now, we will also later look at positive externalities in social and technological networks. Sometimes people also call this the tragedy of commons. In a later lecture, we will talk much more about tragedy of commons and how to deal with that in social and technological networks. Now, one famous special case of interference in the air is so-called near-far problem. If we go back to this picture, you see that a mobile station A is much closer to the base station than mobile station B. Okay? Your neighbor, or your friends, let's say, your friend's iPhone might be much closer than your Android phone to the base station. Maybe your friend is sitting right beneath the cell tower, the base station. And therefore, the distance it traverses is much shorter, and the signal received at the base station is much stronger than yours. And it can drown out your signal. And that is what we call the near-far problem. The near user will overwhelm the farther away user's signal. Now, there was a simple solution provided by Qualcomm in the late 80s that uses the idea of feedback control. Now, later we'll see much more complicated feedback control in a network. In this case, this is a simple one hop from the base station to different mobile stations. The degree of freedom here is exactly transmit power. Okay? And it says that, well, adjust your transmit power based on where you are. It's going to estimate first the channel condition. For example, how much channel loss does your signal suffer? And then it would reverse that. Say if your channel loss is a factor of 2, okay, and the other is a factor of 0.9, for example, okay, then I will tell you, look, you should multiply your signal strength by a factor of 2, and you should multiply by a factor of 1 over 0.9, which is much smaller than 2. Then this power adjustment would cancel out the effect of the channel attenuation, and then I will have equalized received signal power from both of you at the base station. So this is a simple algorithm. There's no iteration, okay? And it is through a central command by the base station. And it suffices to achieve equalization of received signal power. And without this feedback control to take care of the near-far problem, you will never be able to implement CDMA because the amount of interference would be just too much. Now, what if you need to achieve a target signal quality which might be different for different mobile stations? Not just simply equalize all the received power. And that was the challenge in the early 90s. Now, in order to make sense of that question, we have to provide a little bit of symbol. Okay. Now, we're going to look at a very small cell. There are only 2 mobile stations, okay, 2 iPhones, 1 and 2, and 1 base station. Even though there's 1 physical receiver, we're going to divide it into 2 logical receivers. Okay, receiver 1 and receiver 2. And we will look at 4 different channels. 2 of them are the so-called direct channels. These are the desired, intended communication path. Of course, in the air, there's no real physical pipe of a channel. So by channel, we really mean a logical link. What actually happens is just energy propagating in the electromagnetic field and being picked up by antenna. We don't have pipes, as if we're drawing pipes, but we actually don't. So these are logical channels. And we say that there is a transceiver pair from the transmitter 1 to the logical receiver 1, and then from transmitter to logical receiver 2. So happens these 2 logical receivers are physically co-located at the same spot. And then what about interference? When transmitter 1 talks, the energy propagates. Okay? And part of the energy will be picked up by this logical receiver 2. This is a dotted line to represent an interference channel. And there is the other interference channel. And we will use the following symbol, G sub I J, to denote the channel loss on the corresponding direct or interference channel. Now somehow the community got stuck with the term channel gain, even though these G's numbers between 0 and 1. So it should be called channel loss. Let's say they're called channel gains. Now this is a little tricky. So we'll go a little slow here. It says Gij represents the channel gain from the transmitter of the logical transceiver pair J to the receiver of logical transceiver pair I. So we're going to use the terms user, transmitter receiver pair, or logical transceiver pair interchangeably. For example, G11 is the channel from the transmitter of logical pair 1 to the receiver of logical pair 1. Say, well, that's a good channel. Indeed, it is the direct channel for desired communication. And so is G22. So in general, Gii are the direct channels. But when J is not equal to I, for example, G21, that says this is from the transmitter of pair 1 over here to the receiver of pair 2. And therefore, this is the channel gain of an interference channel. G12 says this is from the transmitter of pair 2 to the receiver of pair 1. And in general, G12 is not equal to G21 necessarily. Now, ideally, of course, we want GIIs to be bigger than GIJs, where J is not equal to I. And indeed, with the help of those spreading codes, those ones and minus ones, we do have usually a GII that's bigger than GIJs. However, there could be many J's not equal to I. Okay, there could be tens of them. And even though each one provides just a little bit of interference to your transmission, they could add up. Okay, that is the cocktail party issue again. So how do we capture the notion of received signal quality? If the quality is high, you'll be able to talk more efficiently. For example, you can talk faster and the receiver can still understand what you're talking about. But sometimes in cocktail party, because it's so noisy around, so much interference, you have to slow down your conversation. Okay, you have to talk slower, that is fewer bits per second, so that the receiver can hear you correctly. And the way we capture this ratio is through the so-called SIR, signal to interference plus noise ratio. Now, what is the signal? I'm not talking about the signal power at the transmitter side. I'm talking about the signal power at the receiver side. So that is the transmit power, which we denote by P sub, let's say I, P sub I, multiplied by the channel, that's the direct channel, getting to the receiver of pair I. That's the received power, divided by, this is a ratio of the interference collected at the receiver. That is P sub j times Gij, okay, from jth transmitter to the same common ith receiver. And there are many of such j's not equal to I. Plus, at the ith receiver, there's usually some noise term, n sub I. This is what we call the SIR associated with the ith user. For example, in our previous case, we have just two users, and therefore SIR1 is simply P1 G11 over P2 G12 plus N1. And also SIR2 is just P2 times G22 over interference, which is P1 times G21 plus N2. Okay, but in general, you have more than one term here in the denominator. Okay. So now that we have the notation, let's look at what kind of function this SIR is. SIR for each transceiver pair I, okay, the received signal interference ratio for pair I is really a function of the entire vector, with this notation on top, of power vector P. Okay, it's not just a function of your own power, but also a function of others' power. That is the mathematical representation of the very physical fact of interference in wireless communication. If there's no other user, it's easy to increase SIR for user 1. I'll just increase P1. But of course, there are other users. A larger P1 helps SIR1, but it will also show up as a larger denominator for the other SIRs that will hurt the other SIRs. Okay, so first observation is that SIR is a function of the entire vector P. Now second, what are the constants and what are your degrees of freedom? Because we're talking about transmit power control, so obviously the degree of freedom is the vector P. That's what we want to design and optimize over. We are given all the Gij's. That is determined by the propagation environment. Okay, is this indoor? Is this outdoor? What kind of terrain is it? It is given by the location of the transceivers. And that's not up to us to optimize. And we are given all these receiver electronics and therefore their noise. So the G's and the N's are given constants. The P's are what we'll be calling the optimization variables in transmit power control. So now our goal is to say all different transceiver pairs indexed by I would like to get a certain SIR achieved. Okay, so the question is, for a given set of G's and N's, can we find such a vector P? Is there such a vector P at all to achieve certain target SIR values? And if there's more than one, which one shall we pick? In the next module of the video lecture, we will see the answers to these questions in a distributed mechanism to coordinate interference in wireless cellular networks. And that mechanism is now in use in many wireless standards.